Hello and welcome to this Revision Monkey video on what's going to be in the combined Physics Paper 1 exam for 2023. This is for higher only students and it's for those studying the AQA specification. Firstly, for the 2023 exams, as you are all probably aware, you do not need to recall the physics equations. This is what the equation sheet will look like for your 2023 exams. And it will have all of the equations on there for you. You'll need to use the physics equation sheets by selecting the correct equation. For example, you might have questions that say, write down the equation that links. Let's take this one, for example, write down the equation that links power, energy transferred, and time. So you look down your equation sheet and try and find those words, power, energy transferred and time. So here we've got the equation with all three of those words in. Power equals energy transferred divided by time. So we would copy that straight onto our answer line. 30% of your physics exam is going to be using calculations, and a lot of them will come through these equations. So I'm going to spend a little bit of time on where you're going to get the marks for these equations, because if you can nail these, that's 30% of your exam sorted. So let's have a look at 2 mark calculations first of all. Really, you're getting 1 mark for your working and 1 mark for your correct answer. So we really encourage you to do your working, because even if you use your calculator incorrectly and get the wrong answer, you will still get a mark for the correct working out. So let's have a look at this question. It says calculate the power of a machine that transfers 1000 joules of energy in 10 seconds. So you can use a highlighter in the exam to highlight the question. It says calculate the power of a machine that transfers 1000 joules of energy in 10 seconds. And you've already written down your equation, but if not, you know you're looking for the one with power, energy and time. So you need to write down the equation that you're using, power equals energy transferred over time. Put the numbers into the equation, so power is equal to 1000 divided by 10, and then write your answer on the answer line. If you have a look at a calculation and it is worth 3 marks, you're going to think about it like 1 mark for the working, 1 mark for the correct answer, and 1 mark for something extra. So this could be giving the units, converting the units, significant figures, or perhaps rearranging the equation. So let's have a look at an example where we have to give the units. So if we have the same question again, but this time we are asked to give the unit, power equals energy transferred over time is the equation. Put your numbers into the equation to show you're working, give your answer on the answer line, and then provide the units. So in this case, power is measured in watts. Have a think then and pause the video if you can remember all of the units for the following quantities on the slide. So well done if you remembered power was measured in watts, time in seconds, mass in kilograms, energy in joules, and work done in joules, because they are the same thing. We'll come back to this later, but it's important to remember energy transferred and work done are the same thing. Volume in meters cubed, velocity and speed both in meters per second, height and extension, as they're both measures of distances, they are meters. Charge flow is coulombs, current is amps, potential difference is volts, and resistance is ohms. So they're the key ones that you need to know for paper 1. And the rest of the ones that you need to pay for paper 1, you should be able to work these out using the equations if you can't remember them. So these are the units for density. And you'll get the equation density equals mass divided by volume. So if you remember the units for mass are kilograms, and the units for volume are meters cubed. Then mass divided by volume, or kilograms divided by meters cubed, are the units for density. In the same way, you can work out the units for spring constant. Now, you can actually use the paper 2 equation to work out the units for spring constant, because that will be on the same data sheet. So force is newtons, extension is meters. So if you rearrange this equation, you get spring constant equals force divided by extension. So the units for spring constant are therefore newtons per meters, because that's what you have to do if you're calculating it in that equation. A couple more you can work out this way is gravitational field strength. Again, use the paper 2 equation. Weight is equals to mass times gravitational field strength. If we rearrange that, you get gravitational field strength equals weight, which is measured in newtons, divided by mass, which is measured in kilograms. So the units must be newtons per kilogram. Then specific heat capacity. This is a difficult unit to remember, but if you use the equation, you can work out what it is. Because if you rearrange the equation to get specific heat capacity, which I've just abbreviated to SHC, is equal to energy divided by mass multiplied by temperature. So the units therefore would be joules per kilograms degrees C, because they're the energy in joules divided by kilograms multiplied by the degrees C. And the final ones that you can work out this way rather than remembering is specific latent heat. So if you rearrange this equation, specific latent heat is equal to energy divided by mass. So energy is in joules, mass in kilograms will equal to joules over kilograms. So those are some units that you can work out using the equations if you forget what the units are. So another 3-mark calculation then, rather than giving the units, could be converting the units. So a simple one would be converting minutes to seconds. So this question says calculate the power of a machine that transfers 2,400 joules of energy in 1 minute. So really look out for that. That's a really common thing, and you have to convert that to seconds. So you write down the equation, show your conversion, 1 minute equals 60 seconds in this case, put your numbers in. So rather than 2,400 divided by 1, it's now 60 because you've converted it, and then show your answer. So look out for that in a 3-mark question. It could be that that's where you're getting the extra mark. So the really common unit conversion is the minutes to seconds one. You must multiply by 60 to convert from minutes to seconds. So for example, if you had 1.4 minutes, you would do 1.4 multiplied by 60 to get 84 seconds, and you'd use the number 84 in your equation. Some more difficult ones then are nano. If you see a little n, that means nano, which is times 10 to the minus 9. Micro times 10 to the minus 6. Milli times 10 to the minus 3. Kilo times 10 to the 3. Mega times 10 to the 6. And giga times 10 to the 9. So when these are in front of units, you must do a conversion to get that extra mark. If you can't remember these, then you'll only lose 1 mark, so don't worry about it. But my top tip is leave kilograms well alone, because mass is supposed to be in kilograms. It's supposed to have that kilo prefix in front of it. So leave kilograms alone, but if you see anything else, convert it first. So for example, if you saw 5 milliamps, then you must swap out that milli for times 10 to the minus 3, because that's what milli is, times 10 to the minus 3. So you'd end up with 5 times 10 to the minus 3 amps, which is the same as 0.005 amps. Or if you had a capital M there, that would mean mega. So mega is times 10 to the 6. So you'd have 1.5 times 10 to the 6 volts, which is equal to 1.5 million volts. Another thing to look out for 3-mark calculations is giving your answer in significant figures. So here we've got a similar question, but this time it says give your answer to 2 significant figures, and that's what you'd be getting the 3rd mark for. So you put the equation down, put your numbers in, and you write down your answer as you see it on the calculator, but then it asks you to convert it to 2 significant figures, which in this case, you look at the number here, and because 0.8 is 0.5 or higher, this number here will go up to 47. So our answer is 47 watts. And then finally, you might have to rearrange an equation. So I'm going to give you some clues. If you can't rearrange and find it really difficult, I'll give you the clues to give you the maximum marks on the question. First of all, you need to write down the equation that you're using, and then importantly, write in the numbers that you've got. So this time we've been given the power and we've been given the time, but we don't know the energy transferred. So write down the equation, power equals energy transferred over time. Write in the numbers for power, write in the words for energy transferred, write in the number for time, and then that will at least get you that 1st mark. And then just give it a go at rearranging it. But because we've got divide by 40 this side, we need to multiply both sides by 40, show our working. Energy transferred is equal to 800 multiplied by 40, which is 32,000 joules. So that's another thing that they could do in a 3-mark calculation. And look out for this. If they ask you about energy transferred, look out for a 1-mark question straight afterwards saying calculate the work done by the machine. And your clue is that it is just 1 mark. And if you remember what I said previously, energy transferred and work done are both measured in joules. They are both the same thing. So all that they want you to do on here is write down 32,000 joules, the same as the answer that you've previously worked out. For 4-mark calculations, you might see those on a higher tier paper. You would get your working for 1 mark, your correct answer for another mark, and you might have a couple of these things to do. So you might have to give the units and put the answer in significant figures, or you might have to do a unit conversion and rearrange it. So have a look. If it's a 4-mark question, you're going to be looking for a couple of these things to do throughout the question. If you have a 5 or 6-mark calculation, this is your strong indication that you need to look for everything we've discussed already, and remember that it's probably going to need 2 equations. So you're going to have to look at the equation sheet and think about which 2 equations you need. For example, you might need the power equation and the charge flow equation together to work out your answer for a 5 or 6-mark question. For example, if the question was asking you about charge flow, and if the question gave you a value for power and energy transferred and current, but they didn't give you anything else, then you might need to use the power and the energy transferred to calculate the time. And then you can put the time into this equation along with the current they've given you to then calculate the charge flow. So really strong clue, 5 or 6-mark calculations will often need 2 equations to get the correct answer. Let's have a look at circuit symbols before we move on to the required practicals, because there are a lot of required practicals, the paper one, that involve circuit drawing. So you can pause the video and see if you can remember how to draw each of these components listed on the screen. So first of all, we've got our cell, and the longer line represents the positive and the shorter line the negative. If you have lots of cells together, you make a battery. And then we've got the switches, the open switch and the close switch. You've got the diode. And if you look carefully with the diode, to help you remember, it looks like a D, an I, and an ode. That might help you remember it. And then LED stands for light emitting diode, so that is the diode again, but arrows to show that light is given off. Then you've got the ammeter, the voltmeter, and I've just put motor in, not because you'd necessarily be asked to recall it, but just because you might see it amongst a circuit in an exam question. That is a motor. You've got a lamp, and then to the rectangles. The resistor are the ones with the rectangles. So a normal resistor is just a plain rectangle. A variable resistor has an arrow through it. A fuse is a resistor with a line going straight through it. An LDR is a light dependent resistor. So again, think resistor, I must start with a rectangle, and these arrows show the light going in. So it's dependent on light dependent resistor, as opposed to the diode, which is emitting light. And then finally, the thermistor, like so. The required practicals for Physics Paper 1 are specific heat capacity, density, resistors in series and parallel, resistance of a wire, and IV graphs. In this practical, you'll be calculating the specific heat capacity of a material. And the specific heat capacity is the energy needed to heat 1 kilogram of a substance by 1 degrees C. Now there is an equation to go with this practical, and this equation you're actually given on your data sheet. The equation is E equals m times C times theta, whereby E is energy measured in joules, m is mass measured in kilograms, C is specific heat capacity, measured in joules per kilogram degrees C, and theta is temperature change, measured in degrees Celsius. So the good news is that you don't have to learn this equation. They will give you this one on the equation sheet. However, for this practical, we are going to be calculating specific heat capacity, which is the C part here. Therefore, we need to somehow work out the energy transferred to our material, the mass of our material, and the temperature change. And I'm going to take you step by step through the practical. If you find this practical particularly challenging, I'm going to take you through a simpler method first of all, and then after this, a more difficult one using several equations. So you may want to skip forward to that one if you prefer, or if you'd like a much simpler method, then have a look at this one. So let's say, for example, we have this metal block. That is the material that we want to measure the specific heat capacity of. In the exam, it could be anything like aluminium or copper, or they could talk about a random substance altogether. So the first thing we do is weigh the metal block using a balance and record the mass. So this will give us this part of our equation, the m, the mass. Then we need to wrap our block in insulation to reduce the energy transferred to the surroundings. So you might have some bubble wrap or something like that you would wrap your block in. Next, we place a thermometer in the block, and we need to measure the temperature of the metal block using the thermometer and record it. So this is our starting temperature. We measure our temperature of the block. We then put an immersion heater, which is this heater here. We call it an immersion heater because you put it inside the substance, you immerse it in the substance. We need to plug that into a joule meter over here, and then plug it into a power supply. This joule meter
here will give us our energy transferred to the block. We place the immersion heater inside the metal block and start a timer. Next, we heat it for 10 minutes, and after 10 minutes we read the temperature from the thermometer and record it. And we use this then to calculate the temperature increase. Temperature after minus temperature before gives us the temperature increase. So now we have three values which we can use to calculate the specific heat capacity. We've got the energy that we've got from the joule meter, we've got the mass which we've recorded on the balance, and we have our temperature change which we've recorded using the thermometer. So the final thing we need to do is rearrange that equation on our data sheet to make it specific heat capacity equals, and that would equal energy divided by mass times temperature change. So to do that, we read the energy transferred to the block from the joule meter. That will give us the E like we said, and then we put the numbers into our equation. Specific heat capacity equals energy divided by mass times theta. Now I'm going to move on to a more difficult method that doesn't use a joule meter, which uses a couple of equations to work out the energy transferred to the block. So if you're comfortable with this method, that's great. You can skip to the next required practical. If not, you might want to listen up to the more difficult method, which is coming up straight after. Okay, so we're still on the required practical for measuring the specific heat capacity of a material. This method doesn't use a joule meter, but many of the steps are the same as the simpler method. Again, we're going to focus on this equation on the data sheet, E equals mc theta, which we can rearrange to calculate specific heat capacity. So we still do the same steps as before. Weigh the metal block using a balance to record the mass, wrap the block in insulation to prevent heat transfer to the surroundings, place a thermometer in the block to measure the temperature before. The next step is slightly different, however. This time we're going to plug an immersion heater into a power supply and connect an ammeter here in series to measure the current. We're going to then place an immersion heater inside the metal block and start a timer as we did previously. So rather than a joule meter this time, we've got an ammeter. We're going to heat it for 10 minutes like before, and after 10 minutes read the temperature of the block and calculate the temperature increase. So we've got mass like before, we've got theta, temperature change like before, and what's different is how we're going to calculate energy. So if we've calculated current, you need to use the equation for power. P equals I times V, where I is the current, which is read from the ammeter, and V is the potential difference that you set on your power supply. So using this equation here, we can calculate power by multiplying the reading from the ammeter by the reading that you've set on the power supply for potential difference. Next, we need to use a different equation to calculate energy transferred. That equation is E equals P times T. So P we've calculated from this equation above, and time in seconds is the time that the immersion heater was heating the metal block for. And the final step is then to put it back into this equation. Specific heat capacity equals energy that you've calculated from the two equations divided by the mass times by the temperature change. How does the length of wire affect resistance? Required practical. For this required practical, we need to recall the equation V equals I times R, whereby V stands for potential difference measured in volts, I stands for current measured in amps, and R stands for resistance measured in ohms. And because we want to calculate resistance, later on we'll use the rearranged version of this equation to make sure we've got resistance equals V divided by I. So in this practical, we need to change the length of the wire. That's going to be our independent variable, and we are going to measure resistance, which will be our dependent variable. So the first thing we do is set the power applied to a specific voltage, for example 6 volts. We will connect 2 wires to the power supply and add a crocodile clip to the other ends of the wire. We'll then add an ammeter in here in series, and this will measure current, which is going to be the I part of our equation. We will then attach a length of wire to a meter ruler, so on the ruler like shown, and clip one of the crocodile clips at the 0 centimeters mark. We'll then attach the crocodile clip of the other wire at the 10 centimeters mark, so that the length of wire in the circuit is set to 10 centimeters. We then need to add a voltmeter parallel to the length of wire that we are measuring, and this is going to measure potential difference. We turn on the power supply and record the current from the ammeter, which will give us I. We will record the potential difference from the voltmeter here, and this will give us our V. And finally, we use the equation R equals V divided by I to calculate the resistance across the 10 centimeters piece of wire. To change the length of wire we are measuring, we'll keep the first crocodile clip at 0 and move the other one to 20 centimeters. And then we will repeat as before, taking the readings for current and potential difference and using the equation R equals V divided by I. Now you need to suggest the range of lengths that you are going to use in the experiment, and you need to list them out. For example, repeating the steps above for the following lengths: 30 centimeters, 40 centimeters, 50 centimeters, 60 centimeters, 70 centimeters and 80 centimeters. And then what's really good to do is end by saying that you're going to repeat the experiment by calculating the resistance for each length of wire 3 times and calculate a mean. And if you were to plot a graph of your results, the results that you should see are that as the length of wire increases, the resistance also increases, and a straight line through the origin shows you that the relationship is directly proportional. Resistors in series and parallel, required practical. In this required practical, you are asked to investigate how adding resistors in series circuits or parallel circuits affects the total resistance. For this practical, you also need to recall the equation V equals IR, whereby V stands for potential difference, I for current, and R for resistance. This here is the resistor. I've drawn a circuit here with 2 cells. It may well be 3 cells or 4 cells, or you may have a battery. It doesn't really matter, but something to provide power to your circuit. And you're going to want to attach a voltmeter to measure V, an ammeter to measure I, and you're going to use a calculation to calculate resistance. So we set up a circuit with, suggest 2 cells, an ammeter to measure current, and 1 fixed resistor in series. We connect a voltmeter across the cells to measure potential difference. And we calculate the resistance of the circuit using the equation R equals V from the voltmeter divided by I, which is current from the ammeter. We then add a resistor in series, and when we do this, we're adding the resistor next to the first resistor in exactly the same loop. So we add a resistor in series with the other one, we take new readings for potential difference and current, and then calculate resistance. We will then add another resistor in series with the other two, and again we will repeat the steps to calculate resistance. So if you did add resistors in series like so, you should find that as you add the resistors, the total resistance of the circuit increases. So you might get a graph that looks a little something like that. In fact, the total resistance is actually the sum of all the resistors. So for example, if these were each 5 ohms, our total resistance in the circuit would be 10 ohms. So you can do exactly the same practical, but this time for a parallel circuit. You would start with your initial circuit with one fixed resistor, measuring current, potential difference, and using the equation R equals V divided by I as before. But this time you would add a resistor parallel to the first resistor, which will put it in its own separate branch. Again, you'd measure the readings and calculate resistance, and you'd want to add another resistor, again parallel to the other two, and calculate resistance using the potential difference and current readings. However, in this case, with parallel circuits, you should find that if you add resistors in parallel, the total resistance of the circuit actually decreases, because you can think of it as providing alternative pathways for the electrons, which therefore allows the electrons to flow more easily around the circuit. So in this case, your relationship would be as the number of resistors increases, the total resistance actually decreases. IV graphs required practical. You may well have heard of these called IV graphs or current potential different graphs, with the I standing for current and the V for potential difference. So with these graphs, the circuit that we need to build is all the same. And what we'll be changing is this component here. At the moment, we've got a resistor in the circuit, and we need to be able to change this for a diode and then a filament lamp. So we set up a basic circuit with either some cells or a battery, an ammeter to measure current, a voltmeter to measure potential difference, and this component here is a variable resistor. This allows us to change the resistance of the circuit and therefore the current. So we're going to start off by looking at a circuit to draw an IV graph for a resistor. So our end goal is to be able to draw a graph of current against potential difference and plot all of our results on our graph. To get there, what we need to do is set up the circuit. I've just suggested 2 cells. You might just put a battery in there, or just 1 cell, it doesn't really matter. An ammeter to measure current and a variable resistor. And we're going to start off with a resistor in series. That's just the component that we're looking at. We then connect a voltmeter parallel to the component to measure potential difference. We take the reading for current, which is going to be our I, from the ammeter, and take the reading for potential difference, which is going to be our V for the voltmeter, and plot these on a graph of current against potential difference. You may well say that you're going to put them in a table first and plot them later. Either is fine. We're then going to adjust the variable resistor, which is this component here, and take new readings for current and potential difference. And we're going to repeat this 5 times. So if we adjust this 5 times, it will give us 5 sets of readings for ammeter, which is the current, and 5 sets of readings from the voltmeter, which is potential difference. If we didn't have that, we just get 1 reading from each and we would be stuck. So this gives us a wide range of readings. Up to this point, we would have been able to draw this part of the graph, whereby we've taken readings for current and potential difference, and we've plotted them and drawn a line of best fit. However, we also need to get the negative region of the graph, so we do that using the next step, which is to remove these cells and to replace them into the circuit in the opposite direction. And then we repeat steps 3 and 4 above. And by doing that, we get negative readings for our voltmeter and ammeter, and we can collect data for this negative region of the graph. So that's our completed graph for a resistor at constant temperature. You can see a directly proportional relationship between current and potential difference. If we wanted to replace this component and investigate something else, that's all we would have to do. We'd leave the rest of the circuit the same, and we can replace it with a diode, for example. Now, a diode only lets current flow in one direction, so you'll notice that the graph does not have values in the negative region, and it only has values in the positive region. Finally, you might want to draw an IV graph for a filament lamp, and this graph has a different shape again, because as current increases, the temperature of the filament lamp also increases, so resistance increases. Okay, you can see here the graph tailing off as current gets higher. The trouble is the lamp gets very, very hot, and then the atoms in the wire vibrate more. They are already vibrating because they're a solid, but they vibrate more, making it more difficult for the electrons to flow. So we get this curving off here as the resistance gets really high, so current can't increase at the same rate that it was before. Density of regular and irregular objects required practical. For this practical, we need to recall the equation density equals mass divided by volume, whereby density is measured in kilograms per meters cubed, mass is measured in kilograms, and volume is measured in meters cubed. So if we start by looking at the density of a regular object, here I've got a cuboid. We would measure the length, width and height of the cuboid using a ruler and convert each measurement to the standard unit, which is meters. Multiply the length by the width by the height to calculate the volume in meters cubed, and then we place the object on a balance and measure its mass in kilograms. We finally calculate the density using the equation density equals mass over volume. For irregular objects, we again need to calculate the mass by placing the object on a balance and measuring its mass in kilograms. To find its volume, however, we need to fill a Eureka can, or you may call it a displacement can, with water until it is level with the spout. We will place the Eureka can on a tripod and gauze, and we will place an empty measuring cylinder below the spout. We will then place the object in the can and measure the volume of water displaced into the measuring cylinder and convert this to meters cubed. So then we can put our mass into our equation, divide it by our volume, and we will therefore be able to calculate the density in kilograms per meters cubed of the irregular object.
Okay, let's have a look at some of our top tips then for the content that's coming up. Okay, the particle model is our first topic in the revision guide. Some of the key terms for this topic is you need to know what a system is. So a system is basically the object or objects you're looking at. Now in this case it could just be the water inside the kettle, or it could be a two-object system. It could be the heating element that's at the bottom here. It could be the heating element that's at the bottom, as well as the particles that are inside it. And it will tell you that in the question, but a system is just the thing you're looking at. Okay, well, what's a closed system? So a closed system, just like having a shut door, is where no energy or matter can enter or leave. Okay, so you don't have to worry about any heat coming out or any heat going in or anything like that. Now, internal energy, a really small definition here. Internal energy, the definition for that is it's the total kinetic energy and the potential energy of all the particles in the system. Now, what's this due to? It's due to how quickly the particles move. That's the kind of kinetic energy of the particles. And their state of matter, meaning whether they're solid, liquid, or gas. If they're gas, they've got more potential energy. If they're a solid, they've got less potential energy. Okay, so in our particle model, we can describe, there's certain descriptions that we can give for these particles, and they can also explain their properties as well. So the key ideas of a solid are that the particles vibrate. Now, they're also in a regular arrangement. They're in neat rows. Now, they've got really strong forces of attraction. They're holding onto each other tightly, which explains why it has a fixed shape. The fact it doesn't flow is because they're holding onto each other tightly. They're really close together, and that means I can't squish them in. I can't compress them. So in my liquid, then, the particles are able to flow over each other, which explains why they're in an irregular arrangement. So a little bit more random. They've got weak forces of attraction. Now this explains why they flow to fill the bottom of a container, because they're slightly weaker than solids. And they're still close together, which explains why I still cannot compress a liquid. Okay, you can't squish a liquid. Now key gas ideas then. So particles move in random directions with random speeds. This explains why particles are in an irregular arrangement. They move randomly. There are no forces of attraction. This explains why it fills the whole container when I put it in a box. And the particles are far apart. This explains why it can be compressed. And notice that the ideas of how they behave explains their properties. So the fact that liquids fill the bottom of the container and can't be compressed. Make sure you're matching them up correctly. Okay, so gas pressure then. Gas pressure is caused by particles hitting the walls of the container, and it's a measure of the force per unit area. Okay, so here we have a box with gas particles in it. What is gas pressure? Well, it's when those particles collide with the wall. Okay, so how do we increase gas pressure? In a nutshell, it's making sure you understand this definition here. If I want to increase the gas pressure, what do I have to do? Well, I'm going to need to increase the temperature. Why? So they move faster and hit the wall more often. Reduce the volume, so I make the box smaller with the same number of particles in it. Why would that increase the pressure? Well, what is the pressure? It's the particles hitting the wall. So it must be because they hit the walls more often per unit area. And I can also put more particles in. Why would that increase the gas pressure? Well, because the particles are hitting the wall more, okay, because there are more of them. Okay, a little bit on specific latent heat then. This is an equation that you get given. And I'm just going to refer us to this graph because they do love asking us about this. So this is a heating graph or heating curve. And what we've got along the bottom is time. And so we can think of this as a box with some solid particles in it. In fact, here it is. Here's a box with some solid particles in. And I am heating this box. Okay, I'm heating it with a Bunsen burner, for example. And we can see that when I first start heating it, my temperature goes up. My temperature goes up until something happens. Now, if this was water, the melting point of this would be at 0 degrees C. Here we have my temperature scale up here. So here, my mixture now, my particles are now starting to melt. And so this is the point where melting is happening. Now, there is a certain amount of energy required to melt a solid. Okay, now this, once it's all melted, my temperature is going to keep going back up again. And then once at the very top here, it's going to start to boil. And the temperature of this for liquid water would be 100 degrees C. And then again up here, my temperature is going to go up. So here we can see solid, liquid in the upslope and gas in the upslope there. And these flat parts, well, what is the heat being used for? What is the energy that's going into it? What's it doing? Well, the energy is breaking the bonds. As we can see here, the energy is being supplied to change the state. So here we go. This is the energy needed to change the state on these sections here, how much energy is put in. So there are two different types of specific latent heat. One for this one here, and one for this one here. So the latent heat of vaporization is the energy needed to boil 1 kg of substance. So remember, vaporization, making a vapor, making a gas, is to do with the boiling. And the latent heat of fusion is to do with melting. And think fusion, you're fusing things together, so kind of the opposite of melting. Energy then, top tips for transferring energy between stores, if I can say it. So an important rule here in the energy topic, energy can't be created, it can't be destroyed. You can't magic energy out of nothing, you can't make it disappear. You can only transfer it from one store to another. Now, every time energy is transferred, there will be some wasted energy, usually heat, which warms up the surrounding air. So nearly all machines waste heat in one form or another, whether it be electrical heat generated or friction. So let's have a look at this example of transfers of energy. Let's say I've got a big roller coaster ride here and I want to place a car up on the top. Now, the work done that I use to lift that car, how much energy it takes me to lift it, is the energy that goes into the car in its gravitational potential energy store. So when I lift it, it's going to have its maximum gravitational potential energy at the top. And there he is, ready to go. Okay, as he starts to go down there, now EP equals mgh. As he starts to go down the hill, the height goes down. That means that the potential energy goes down. Where's it going to? It's going to turn into the gravitational potential energy store decreases and the kinetic energy store increases. So we can see that my Ke, which equals a half mv squared, will start to go up. My kinetic energy starts to go up. Why? Because my velocity starts to go up as he goes down the hill. Okay, at the bottom of the hill, he's going to have his maximum kinetic energy. He's at his maximum speed at the bottom of the hill. Now, down here, he's going to hit the brakes. The brakes are going to get red hot and the car's going to stop. Now, the kinetic energy store decreases. okay, his kinetic energy store is going to disappear as the thermal store in the brakes increases due to the heat from the friction. Okay, and each time it's the same amount, exactly the same value. So for example, if I said that the work goes in was 5 joules, well then his gravitational potential energy equals 5 joules. His kinetic energy at the bottom here would be equal to 5 joules. And the work done released as heat would be equal to 5 joules as well. Okay, so the energy is transferred each time. Now we're being a bit generous here, that there would be some wasted energy each time, but for simplicity we'll just ignore that. Okay, a little bit more about energy then. So imagine you were going to be asked to compare the cost effectiveness of 2 different types of appliance. So it could be bulbs, it could be fridges, could be anything else. Now they love asking about cost effectiveness. So let's have a look at this data here. We've got 2 types of bulb, Solaro and Luxmore. Here's their cost to buy. Here's how long they last, their lifetime. And this is their running costs per year. Okay, typical question then. Compare the cost effectiveness of the 2 types of bulb over a 10-year period. That is a really important thing. Compare, so stick a box around that, and we want to compare the cost effectiveness. So you need to work out the entire price of buying enough bulbs over the period and the running costs over that period as well. So you've got to buy enough bulbs and you've got to work out the running costs over that 10-year period. That way you'll know basically which is cheaper, which is more cost effective. Okay, so let's do exactly that then. So the first thing we're going to do is look at the first bulb and we're going to say, what is the total cost for it? Well, how many of those will you need to buy to cover 10 years? And how much are the running costs going to be for 10 years? Now, you're going to need, because it only lasts 1 year, you're going to need 10 of those. These ones, running cost per year, you're going to need 10 of that as well. And similar for Luxmore, for the other one, this one lasts 2 years. Each bulb lasts 2 years. So if I want to cover a 10-year period, I need 5 of those. But the running costs are still per year, so I'll need 10 of those. So here's my calculations then. Cost of the bulb, £1.50 times 10. You can see up here. Running costs, £2.50 times 10. So I add those 2 values together, making Solaro bulbs cost £40 over 10 years. Next, Luxmore bulbs, £2.50 times 5. It's 5 because each one lasts for 2 years and I've got to cover 10 years. So £2.50 times 5. Running costs, 50p times 10 years, giving me a total of, just adding those 2 values together, £17.50. Okay, so I can see my conclusion is Luxmore bulbs are more cost effective. Okay, energy resources and their uses. This is your renewable energies, non-renewable energies, that sort of thing. Renewable energies then, definition, they won't run out. Non-renewable, they will run out. Okay, so I'll put them into a few different categories. Let's look at some of these names here. Solar power, wind power, wave power, hydroelectricity. If you're not sure what that one is, hydro is kind of like a Greek word for water. That's falling water, so damming up rivers. Biofuels, bio meaning living things, so it's crops and wood. Tidal power, that's our tides going in and out twice a day based on the moon that goes around our planet. And geothermal, geo meaning earth and thermal meaning hot, so this is hot rocks under the ground. Okay, now some key points here. These ones are, renewable ones are free energy. Really worth saying that once it's set up, it's free. They're not always reliable. So which ones are not reliable? Solar, wind, wave, they all depend on the weather. Now these next ones could really be described as reliable. Geothermal only works in certain places though. You might need lots of them to supply our energy needs. Okay, you'll need thousands of wind turbines to replace a coal power station, for example. Okay, non-renewable. So these are our fossil fuels. From the dead remains of plants and animals from millions of years ago. These will run out. We dig them out of the ground. A couple of key problems with this: damage to the environment, producing carbon dioxide, name it. Okay, don't say polluting gases, name it. You know the name of it, call it carbon dioxide. What does it cause? Global warming. Now at the minute, these provide most of our energy needs. And that's an important thing for you to know. Okay, at the minute we use mostly these. Okay, why do we use mostly these? Well, they are reliable. You know, they're always going to be there. They can supply most of our demand. Non-renewable, there's one other non-renewable one, which isn't a fossil fuel, but it will run out one day, is nuclear. And why does it run out? It's because we dig the fuel out of the ground, uranium. Okay, and there's only so much uranium on our planet, but it will last thousands of years. Now, a good thing about this, you get lots of energy from a small mass of fuel. That means we don't need lots of transport, carrying train loads of coal up and down the country, or pipes carrying gas up and down. Now, there is a small risk of disaster. If the disaster happens, the disaster is pretty bad, like Chernobyl, the Russian Ukrainian power station that blew up in the 80s. And the good thing about this is there's no polluting gases, so no CO2, okay, when the electricity is being made. Okay, on to the electricity topic. We've covered a lot of this already in the required practicals. So here we're just going to cover a few things to do with electrical safety. Now, a few key things for you to know here. The UK main supply, so what we get out of plugs, is AC. Now, if I was to draw that on a graph there, alternating current. So the voltage goes backwards and forwards, and the current does go backwards and forwards. Potential difference is 230 volts. You just got to remember that for 24 hours and you'll never need to know it again. 230 volts. And our frequency is 50 hertz. Okay, a few things about our plug then. Now, the color of these wires on the plug tells us where they go. So the live one is brown. The earth wire is striped. Our neutral wire is blue. And you can probably tell from the way I've written it, the second letter, it tells you where it goes. So we've got blue on the left, we've got striped at the top, we've got brown on the right. Okay, a few bits of safety to do with this then. So the live wire, that provides the alternating current and it carries a voltage of 230 volts on it. It can give you a shock if you touch it. This neutral wire here, what's its job? Well, it completes the circuit. Just like in a traditional circuit with a bulb, you'd never try and light a bulb up with just the live wire. You would need to also have a wire that returned it back to the cell as well. Okay, what about this earth wire then? So it's not involved in sending electricity to the component or back again, but it does, inside the machine, it connects to the metal case. So something like a fridge or an oven or a freezer, if the live wire inside comes loose and touches the metal case, well, instead of going through you, the current flows down the earth wire, not through you. And that's because it has a really low resistance. Okay, and electricity wants to take the path of least resistance, so it goes down the earth wire, not you. Now, here's a question, typical question. Engineer's fixing a plug socket. He has switched the switch to the off position. Explain how the electrician can still get a shock. Okay, well, there's a large potential difference in the live wire, 230 volts. The man will provide a path for the current to go to ground. The current will flow through him, giving him a shock. Okay, two components you need to know a little bit more about, LDRs and thermistors. Here are the examples for them. So example is a street light. On the top there is an LDR. Thermistors will be in a thermostat or also in a kettle or oven. Here are their circuit symbols for them both. And you need to know the relationship between, in this case for an LDR, light, and for thermistor, temp. You need to know the relationship between those things and its job of changing the resistance. So here's the first one. Okay, so for an LDR, when I have, as I increase the light, the resistance goes down. Okay, it's got that shape of graph, inversely proportional, and exactly the same again for thermistor. So when we have lots of heat and it's hot, we have a low resistance. Now, should you be asked to explain how to place an LDR into a circuit, if you want an LDR to decide when a light comes on, well, you need to place the LDR in parallel to the bulb. So here it is. Okay, I'm back to my cell. Excuse the slightly childish drawing there. So I'm placing my LDR in parallel to the light so that when it's daylight, and we don't want the bulb to be lighting up in daylight you're going to have a low resistance in the LDR. If this has a low resistance, the light will pass through it. Sorry, the electricity will pass through it. The electricity will pass through here, not through the bulb, meaning the bulb stays off in daylight. So off in daylight. Now the opposite would happen at nighttime. So at nighttime, you can see from the graph here that at nighttime we would have low light, we would have a high resistance on the LDR, meaning that the electricity can't go through the LDR, it will go through the bulb instead. So it will be on in daylight. Now for a thermistor, it really does depend whether you're going to turn on a cooling device or turn on a heater as to whether it wants to be in series or parallel. Okay, national grid. So the national grid, we don't need to know loads about this, but this part is the national grid. So this is a diagram showing us a power station, step-up transformer, pylons, cables, step-down transformer are homes. The national grid is a series of cables and step-up and step-down transformers. That makes the national grid. So power stations and houses are not included. Now, what do we need to know about step-up and step-down transformers? Well, we need to know that a step-up transformer increases the voltage to reduce the energy loss in the cables. Okay, so we need to increase the voltage. So a nice way of thinking about that is step up. Okay, U is next to V in the alphabet. That's how we remember that step up increases voltage. Okay, and both of these refer to voltage. So step up, increase the voltage, reduce the energy lost as heat in the cables. And here we have the step down transformer. Why? It makes it safe to go back into the house so that we don't die should we accidentally get an electric shock. Okay, onto the radiation atomic structure topic. Let's start with our gold leaf scattering experiment. So this is Rutherford's gold leaf alpha particle scattering experiment. We're going to start off with the plum pudding model. Plum pudding, large sphere of positive charge. Okay, electrons randomly scattered inside. Now, what was the experiment then? So they wanted to fire alpha particles. This is my source of alpha particles here. They wanted to fire it at a thin layer of gold leaf. So here is my gold leaf, side on. Gold leaf is great because you can make it 1 or 2 atoms thick. Now, they wanted to fire these alpha particles through it. What did they expect would happen? They expected that nearly all of the alpha particles would pass straight through. Okay, well, what did they actually find? They found that most did pass straight through, but some were deflected a little bit. And this one, they're really unexpected. Very few, a tiny number, deflected back to the source. They actually rebounded back to where they came from. Now, this proved to us that this model couldn't be right. And this is what it did prove. So the fact that most pass straight through can only be explained because our new model of the atom says it's mostly empty space. Some deflected just a little bit, and that's because we're firing positive alpha particles at a positively charged nucleus. And when they get close, they will deflect a little bit. And then just a few that were fired straight at the nuclei rebounded back, which tells us that the nucleus is very small. It's tiny, and it has a concentrated mass. So this is how we describe the nuclear model. Mostly empty space, positively charged nucleus. The nucleus is small and has concentrated mass. Okay, so here we have our nuclear model. Our electrons orbit in shells or energy levels. And we can also say some properties of we can also describe the properties of some of these particles. Now, don't be scared by this word here. Subatomic just means proton, electron, neutron. Okay, you know those really well. Don't worry about that word there. That's what it means. So we know the relative charge of these things. Now, protons are positive, +1. Neutrons are neutral, 0, meaning electrons are -1. Now, the relative mass of these, all of the mass of an atom is found in the nucleus. So what's in the nucleus? Proton has a mass of 1, neutron has a mass of 1, electron very small. Okay, we have here our symbol from the periodic table. This is the same as in chemistry, this part of the topic. Our top number is our mass number. That's our total, protons and neutrons. Bottom number is just the atomic number. That's just the number of protons, which also happens to be the same as the number of electrons. If I want to find the number of neutrons, I've got to find the difference between these two numbers here. So top number or bigger number, take away smaller number. Now, an isotope is a different number of neutrons, but the same number of protons. So lithium-8, for example, has 1 more neutron, same number of protons. So here's my proton number. They both got 3. This one here has got 4 neutrons. That one there has got 5 neutrons. Okay, nuclear radiation, though, are alpha, beta, and gamma. Let's have a quick look at some of these examples here. Well, what is alpha radiation made of? It's a helium nucleus, 2 protons, 2 neutrons. Because it's 2 protons, 2 neutrons, it's got a +2 charge. Beta particles, what do we know about that? It's a high energy electron from the nucleus, and it has a -1 charge because it's an electron. And gamma radiation is an EM wave, doesn't have any charge because it's not a particle. Okay, what else do we need to know? What are they stopped by? Alpha radiation stopped by paper. Beta radiation stopped by thin layer of aluminium. Gamma radiation stopped by thick lead. Now, we also need to know their ionizing power. That means stripping electrons from atoms. Alpha radiation is the most highly ionizing. Makes sense because it's the most highly charged. Gamma radiation is not really very ionizing at all. Can be dangerous in large levels, though, of course, because it can pass straight through you. So our range in these in air, well, less than 5 centimeters for alpha. So on the outside of your body, really quite safe. Inside of your body, awful. Range in air for gamma radiation is over kilometers. Okay, now should we put them into an electric field, they will be deflected, they'll be attracted to the different charge plates. So beta particles are negative, that's why they go to the positive. Alpha particles are positively charged, so that's why they go to the negative plate. And gamma radiation, no charge, so goes straight through. Okay, half-life. Half-life of a radioactive material is the time taken for the radioactive count rate to go down by half, how many counts it's giving out per second. It's the time taken for the number of radioactive atoms to go down by half. So there's a couple of skills here they're going to ask you to do. The count rate or the radioactivity of any radioactive substance goes down over time, just gets less and less. So let's have a look at the half-life of a material. Let's say material X has a half-life of 2 years. The count rate starts at 240 counts per second. That's CPS there, starts at 240 counts per second. Now, after 2 years, it's going to go down to 120. After another 2 years, it's going to go down to 60, noticing it's going down by half. Then after another 2 years, it goes down by half again. Then the next one will be 15. Now, that could be one of the skills, working out what the count rate would be after a certain number of years. Just write down, just halve it each time and count how many times it's halved. Now, the skill that they may well ask you is they'll show you a graph and they'll say, find the half-life. So I've got 2 graphs here. How to find the half-life from a graph? The first thing to do is, what is my starting count rate or my number of nuclei? So here we've got the count rates per second. We're starting at 80. Here we've got the number of nuclei, the number of radioactive atoms starts off at 100. So there's my starting rate on both these graphs. Halve it. So here we go, 100 down to 50. And just at the same time, I'll do this one as well. So here's 80 down to 40, so I've halved it. I'm going to now draw a line to the graph, to the line, and draw down to time. So here we go. So across from 50, that looks to me to be about 10. So my half-life here, that is my half-life, is 10 seconds. And here, I'm going to draw it across to here, and it looks like that should be just slightly less than 2. Now, be prepared on these graphs. This is not the type of graph that you'll have in your exams. Be prepared that you have to be accurate to within half a square. That's about half a millimeter on your graphs. And so nuclear decay equations then. These look rather scary down here. I've got some already written out for us. Now, alpha, beta, and gamma radiation are all emitted by the nucleus. And a neutron can also be emitted during decay. So each one of those could be called radioactive decay. Isotopes that are unstable will release alpha, beta, or gamma radiation. So here's some examples. You're going to have to find the new mass number or the new atomic numbers. So let's have a go at this. What are the golden rules to this then? First golden rule is the top numbers must balance on both sides of the arrow. So let's look at this first one, 2, 3, 5. On the left of the arrow, on the right of the arrow, 4. So I want to know, what is that number? Well, if they need to balance, 2, 3, 5, it's going to have to be the same as some number plus 4. So 2, 3, 5 minus 4 is going to give me 2, 3, 1. Now also the bottom numbers must balance on both sides of the arrow. So this is for beta radiation being given out, and beta radiation shows that I'm going to have 14 on the left, a 0 there, meaning that must be 14 too as well. And over here we've got 6, and this needs to balance with something minus 1. Well, what minus 1 would equal 6? That's going to be 7. Okay, so the effect of beta radiation is it makes the atomic number go up by 1. It makes the mass number stay the same. What's the effect of alpha radiation? Mass number goes down by 4, and the mass number goes down by 2. Gamma radiation is lovely, no change. Okay, irradiation and contamination then. So if I irradiate something, it's like me shining a torch of alpha, beta, or gamma radiation at something. It's useful for sterilizing medical equipment or treating cancer. Now, it can come out in a stream and it can hit an object. That object is not radioactive afterwards or dangerous. Of course it's not, because it can be used for more operations, for example, if you're sterilizing equipment. So just a couple of pictures of those. This would be them sterilizing medical equipment. This will be them treating cancer. So contamination is different. You need to know these definitions here. Contamination means when you get a radioactive source on you, radioactive atoms on you, attached to you, and then they can then release dangerous alpha, beta, and gamma. Now, this can be useful if you want to see inside a human during a medical checkup. So you might drink a barium liquid to be able to see inside the stomach, or maybe put some radioactive material through a water pipe to be able to look for leaks. So here is the inside of someone's intestine, having drunk a radioactive liquid. And here is some radioactive material going through a pipe to be able to detect leaks. Now, the properties of these that they're going to use will depend on what you want to achieve. So you definitely don't want to hurt a human to be able to see inside them. So you're going to want a short half-life. Okay, you're going to want that to leave your system quite quickly. Okay, so a short half-life on that. Okay, so first off in the higher tier combined part, you might need to describe a way to increase the efficiency of an intended energy transfer. So here we've got adding oil to moving parts to reduce friction, okay, or adding insulation to a heating device, so a kettle or a water heater up in someone's loft. By adding these two things to those two different processes, well, what are you doing? Well, you're just reducing the energy that's lost to the surroundings as heat. So friction would cause heat energy to be wasted. So adding oil just reduces that friction, and adding thermal insulation just traps heat in a little bit more as well. Okay, so you may also be asked to calculate the net decline expressed as a ratio in a radioactive emission after a given number of half-lives. Sounds scary, it really isn't. So let's have a look at this. Half-life is the amount of time it takes for the radioactive emissions to go down by half. Let's say we start off with 240 counts per second. After one half-life, 120, then 60, then 30. How do we express this as a ratio then? Well, I've expressed it as a ratio and a percentage just to have it all down there. So the decline, that means the reduction, expressed as a percentage. So at the start, we've got 0% decayed. So what would that be? 0 out of 240. After one half-life, half of them have decayed, 120 out of 240. So what would that be as a ratio? 1 to 2. 50% have decayed. So let's get rid of that. After two half-lives, now after one half-life, there was 120 left, and that 120 left has decayed again, meaning 180 have now decayed. So that is our showing our net decline. That's what we've lost, meaning 75% have decayed. And then again, 210 out of 240, etc. Okay, so this is us just expressing our net decline, as in how much has it gone down to compared to with the original. Okay, now you may also see it on a graph. This is a nice way of looking at it. We've got here the number of daughter atoms. The daughter is the product after it's decayed, compared to the number that we started with. Now, let's say we started with 240 million atoms. Well, then after one half-life, we're going to have 120 million atoms. And as a ratio, that would be 0.5. Okay, so after one half-life, we're down to 0.5. After another half-life, well, we've lost half of the half. So now we're up to 0.75. Okay, and just like the numbers were before on the last screen, we're now up to 0.875 and so on. Okay, just expressing the ratio of how many we've lost compared to what we started with.